Thank you so much, Professor. Thanks for agreeing to do this interview. Would you tell us a little bit about your educational background? Let's start from high school. When did you go to school?
I was born in West Virginia, and actually in Princeton, West Virginia, which is pretty much the southernmost part of West Virginia, and lived there through junior high. Currently, people call that middle school. And then at that point, my family moved to North Carolina in the Mooresville area, which is about 30 miles north of Charlotte. And so it's in the Piedmont of North Carolina. And I went to high school there. And I was kind of lucky in some sense. Certainly at that time, and I do very well remember having very good experiences in school in West Virginia, in elementary school. In fact, I can name all my teachers if you want me to name.
Not that.
No, I'm not going to. But, and also in junior high school, I think I was very fortunate to have some very good science and math teachers and so forth. And then, so, I mean, they really did pay a lot of attention and to detail. And I mean, it was a no-nonsense experience, I guess. And then we moved to North Carolina, and the high school experience there was a little different, but I certainly benefited from a really good science teacher. It was a small high school, actually, so I had the same science teacher for biology, chemistry, and physics. The same guy all 3 years. But he was pretty well focused and everything, and very good, actually. Actually, and then some of the other memorable teachers were actually my English teachers. Especially one who actually made it very, very interesting. So I think I was quite fortunate there. And so after that, I went to a small university in North Carolina for undergraduate. It's called Western Carolina. It's up in the mountains of North Carolina. And it was really, truly a very good experience for me because one, I like mountains. And secondly, it was a small physics program at that time. So they were certainly, you certainly got attention. Let's put it that way. You couldn't hide anywhere. And they were very, very nice. So they had some very good teachers. It wasn't a research level university. It was basically a teaching university. So that was their focus. So I think I benefited from that. And they made it very interesting, very hands-on, kind of oriented. So after that, I was looking for graduate schools, and I looked mostly in the Northeast and the Southeast. And I visited these places. I think I applied to 6 places, got into all of them and everything. But I went on visits to them, and for some reason, I still don't know it. You know, it's like magic, I guess. I really enjoyed my visit at William and Mary. And so I decided to go there.
Oh, excuse me, the distance between this university and the place you were living, was it close? I want to see why you decided to visit this place, this university. Or maybe I should ask in this way, that at the time, it was pre-internet era, right? You didn't have any information about, I mean, you had limited information most probably. You couldn't, at your convenience of your room, I mean in your house, you do research about these universities and decide which one you should choose. I want to know what was your logic at the time, generally, how students make a decision about their university.
Yeah, it's hard to say. I'm sure everybody comes to it a different way, but at that time, of course, you know, I don't know if modern students will relate to this at all. You're right. There was no internet for me to go on there and just get a quick overview of places. What these schools would do is they would mail you stuff in the mail, And they'd also mail departments flyers and things like that. And usually they had a postcard you could tear off and get more information. So the flyer itself would have some general information about, what their specialties were and things like that. And then you would send in this postcard or something, and then they'd mail you a big packet that would have more detail in it. So that's what I did. And at that time, I think that's what most people wound up doing. And so I narrowed it down to, I think, 6 places, primarily because I think at that time, you had to take the GRE exam. Yeah. And I think you got, at that time, maybe 3 for free, and then you had to pay for the next 3 or something. So 6 seemed like enough. And I figured, well, what's the point? I'm not applying to 100 of these places. So, and geographically, I sort of had settled on the northern states and the South, well, North Carolina and above, let's put it that way. And I'm sure I sent out more than 6 flights, asked for information from more than 6 places, but after I got it, I just looked at those 6, and so I narrowed it down to those 6. And I visited, so I was invited to visit all these places, and I did, but it really came down, you just have a gut feeling sometimes. Yeah. And so after I visited some of these places, and it did come down to a tough decision, to be honest. There are 2 places that I really had a tough time choosing between, but eventually I chose William and Mary. A little side story there. I remember when I visited there, and at that time you'd visit, and then they would show you the department. You'd visit with the faculty, and oftentimes they would send you off to lunch with the graduate students so you could ask graduate students things that, without a faculty member present or something. And so I remember going to lunch, and so I thought all these people were, because they all look very young, I thought they were all graduate students. Yeah. And so I asked, it's kind of funny thing. So I asked this question, well, what do do the faculty get along? I mean, is this a nice place to be? Because I didn't want to be in a place where there's a lot of tension or anything like that. And it was kind of funny because it got kind of quiet. They had been talking before. And finally, one of them spoke up and said, well, I'm not a graduate student, I'm a faculty member. And he went on to give his view of the faculty and everything, which was, I think, quite accurate. It was a very good place. That people got along and they focused on their work and and everything. Turned out that faculty member at that lunch was Mark Conradi. Okay. And you have to remember, he was very young at that time. That was his first position. So, and he I think had only been there a couple years, so he wasn't that far removed from his postdoc. So, that's probably why I didn't think of him as a faculty member, just another graduate student, and so forth.
Okay, so why physics? Why did you decide to choose physics as your major?
Well, for as long as I can remember, I knew I was going to do science and something. I was always fascinated by science, and I had a gut feeling that's what I would do. And it just, you gravitate towards certain things. Yeah. And I find most things interesting, whether it's science or not. But I just had this inclination towards it, I guess. And it certainly helped to have good teachers and people that's excited about it, and you see it. But I think part of it is, of course, there's many sciences, right? And I think part of it was that it just seemed more like you could actually calculate things, and there was no guessing. You either got it or you didn't. There's no, if you make a calculation and somebody else can't reproduce it, then it's not right, right? Yeah. And so it's testable very easily and so forth. And maybe it's just more, in my mind, it was just more straightforward and logical. And, the starting point, you work toward an end. But I think it was just, that was part of it. You know, I'm certainly not a biologist. I do enjoy walking around in the woods and things like that, but I don't memorize things very well. So I didn't think biology would be the way to go. I'm not saying that all the biology is just memorization. But in high school, that did appear to be what it was to me at the time. So, you know, as I got older and you start seeing, you know, higher level biology, it's clearly more detailed than that. But I think it was just the logic of it, and it just seemed to tie together, and it's kind of somewhat easy to visualize, I think, for me. So.
I see. So at the time, did you know what would be your career in the future when you were doing your study? I mean, when you were a bachelor student or graduate student?
I did not have a clue. Okay. To be honest, I went to, you know, to college, I'd lived in small towns. And again, this is like you said, this is the pre-internet world.
Yeah.
You know, your worldview is pretty much the town you live in oftentimes. And so if you think about it, if you're in a small town, what do you see? You see teachers, and you see factory workers, and you know, if you're lucky, you don't see a doctor, but you're aware that they're there.
Yeah.
Right. So you really don't see. It's not like you walk down the streets of the towns I grew up in and you'd see a physicist that you could bump into and talk physics. And there was an observatory there. There was no college in either of the towns that I grew up in. So you're not really aware that much of what the world holds in some sense. You know that there's stuff there from your, you know, what your teachers tell you and everything, right?
Yeah.
You know, that discoveries are made, but you don't have firsthand knowledge of it and so forth. So in that sense, it's a little difficult to decide what you want to do. So, you know, keeping that in mind, and you think, so I go to, I'll be honest, so when I was in high school, I worked summers in a textile mill, you know, to make money.
Yeah.
And I worked every summer. And sometimes it was in a grocery store, but I'd worked every summer in a textile mill. And in college, I wound up coming back and making money in summers working in textile mills were big in North Carolina at that time. They're kind of hard to find now. Most of them disappeared and moved out. But when I was growing up, if you wanted a job, you could just basically walk to a textile mill and you had a job that day. And it was all very hard work. I didn't mind it. But, you know, at some point you think, I don't think I want to do this for 30 or 40 years either. Now, I do admire the people that do that because, you know, they're providing for their families and things.
Yeah.
But I could tell you, a couple summers, I worked in what you could bona fidely, clearly call a sweatshop because there was no air conditioning. And in North Carolina, it gets super hot, and you're in a factory with a lot of machines. It's very hot. Yeah. I mean, you really know what work is. One year I got lucky and it was an air-conditioned factory. Wasn't so bad, but still was very hard work. Yeah. But anyway, so I go to, so I decided, well, maybe, you know, definitely I think I want to go to college to see what else is there, right? Yeah. And but even in college, you know, I wasn't really, I remember going in thinking that, okay, I'm going to major in physics. Right. Yeah. Well, actually, at that point, I didn't know if it was going to be chemistry or physics. I just knew it was going to be one of those sciences. All right. And very quickly, my freshman year, I decided that it was going to be physics. And although, to be honest, I had a fantastic professor for freshman chemistry. And but I decided, yeah, I think I think physics would fit me better. Let's put it that way. Yeah. I probably won't hurt myself there. Yeah. Started there, and I'll be honest. I have no idea how I wound up in Mark Conradi's group. I think it was magic. It's almost as if I remember waking up one day and soldering circuit boards for his group, and I'm like, I really don't know how that worked out, but I'm grateful it did. So, so I did talk to other faculty members when I was there, but somehow I just wound up in his group, I guess, and really did learn a lot,
Yeah.
and everything.
Yeah. I also talked to Mark Conradi. I didn't know at the time. I mean, when I wanted to contact you, I mean, when I was researching about you, uh, I didn't know that you actually did your PhD in his group. So I so what did you do in during your PhD? What was your PhD thesis about?
Yeah, so the benefit of working in Mark's group was I actually worked on several projects.
Mm-hmm.
At that time, and I think even today he still has interest in these things, but he was heavily involved in molecular crystals and molecular motions and things like that in solid materials. And so I worked on things like ring flips and paraterphenyl, uh, self-diffusion in benzene, in solid benzene, and then my thesis was actually on self-diffusion in aluminum metal, trying to extract out the energy of migration and the energy of formation that you need to know in order to determine how fast things are diffusing in a solid material. So that was what my thesis was on, and it was actually a very interesting experiment to extract that. When you measure diffusion, it's very easy to get, say, an activation energy, and just measure the jump times and things like that as a function of temperature, and you can extract it out. But that the nice thing about working with Mark was, and he had many other graduate students as well, is that what it showed you was that because he'd used different techniques, and you very quickly learn that it's not you can be clever in how you do things. It's not just about sticking a sample in a magnet and taking a spectrum and see what you get, but you can manipulate things. And so just like you can manipulate Hamiltonians, you can manipulate the experimental conditions in funny ways to get the information that you're really after. And I think it's in many ways the biggest thing I learned. In fact, all the NMR basically I know came out of working with Mark.
Mm-hmm.
But it was really that idea that you got a problem. How do you adjust the NMR experiment to be able to extract the information that you want? And and even at that time, there are lots of techniques to do that. Well, maybe not as many as today, of course, but you'd use different things. different methods and get some very novel information that way. Yeah. The other beautiful thing about working in Mark's group at that time was I think there was no better way to learn what a pulse sequence is than working with his spectrometer, because his spectrometer was completely home built. And the way that you did a pulse sequence, unlike today where you sit at a keyboard and you key it into your spectrometer, right?
Yeah.
At that time, what he had was timing circuits, and you use patch cords, right? And so you would set a timer for a pulse, and you would patch cord that over to a delay line. In other words, the pulse sequence consisted of basically you wiring it together. But you use patch cords, so the basic timing circuits were already there, and you patch things, and then with an oscilloscope, you would adjust the timing. So again, unlike today, where you just go to the keyboard and say, I want the spacing between these pulses to be 5 microseconds or something, you patch cord this over, and on an oscilloscope, you measured 5 microseconds or whatever it was, and you did that for the whole pulse sequence. So you basically hand-wired your pulse sequence.
It's interesting. I was talking to other graduate students in my department, in our department, when and I was talking about the NMR course, and they said, yeah, it's very abstract, and nowadays, yeah, as you mentioned, we just use a keyboard to just command what we are going to do, what we want to do. But when the way that you learned it, it's not abstract. I think it's very, very physical things. You can touch the oscilloscope, you can touch the wiring and all these things.
Now, and having said that, now, Mark taught an NMR course, and the book we used, of course, was the book by Charles Slichter. And, that's a very heavy book to use. But Mark was very good at bringing it to life. I'll say it that way. He's very animated. He made you understand. He would use hand gestures and things like that to make you understand exactly what was going on. So it wasn't like just memorize a bunch of equations or try to understand them. He would actually put them into action, and if that's a good way to say it. And I think it gave us a better intuitive feeling for what was going on there.
When did you do your PhD? I mean, when did you start it, and how long did it take?
I think you're asking me to remember a lot of things. I think I started in the fall of '81, I think. And I defended probably in December of '87.
Okay.
I had a couple little travel things in between that, which I won't go into. But yeah, I think those are the dates.
Okay. And what did you do after that? I mean, did you do a postdoc?
Yeah. So after that, I was trying to decide what to do, and Mark suggested maybe looking into a postdoc, and he pointed out that Jake Schaefer was looking for one. I didn't know. Again, there was no internet, so I think at that time faculty members just contacted other faculty members by mail or whatever, phone calls and things like that, and say, hey, or at a conference, you bump into people, say, yeah, I got an opening. If you know anybody, word of mouth kind of things. And so Mark relayed to me that he was looking for a postdoc, and so I applied. And I'm not even sure what the application procedure was at this now. I don't know what it was. And at that time, and let's see. So the only thing I knew about Jake at that time was that he was doing polymers, synthetic polymers. And I didn't know anything else about it, to be honest. And so I applied, and a little bit of history here. So when I defended, Mark had already moved to Washington University. So he started off at William & Mary, and then he moved to Washington University and joined the physics department there. So that may have weighed a little bit in my decision, because Jake was so Washington University is in St. Louis. Okay. Now, at that time, Jake was still at Monsanto Corporation. And I think the suburb is Creve Coeur, so just outside of St. Louis. And but he was getting ready to move to Washington University to join the chemistry faculty. He'd been at Monsanto a very long time, and but he was moving to Washington University. And so anyway, so I applied, and so Jake took me in. And at that time, his lab was still at Monsanto. And so that's where I started working, and went there. And of course, Mark had told me that he was doing magic angle spinning, high resolution solid state. So I knew a little bit about it when I went there. And so anyway, so I joined up with him and started off at Monsanto. Now, we were only there for a few months, maybe 6 months to a year. I can't quite remember. It was a transition period. I knew he was going to Washington University, but they had to build his lab and everything else, and so forth. So it wasn't like he just took it and one day you jump over. So he was very methodical in the way it moved. And so when I joined, we were there at Monsanto, and there was another postdoc that had just joined, Vince Bork, and he was there before me by a few months or something. And so at that time, Jake's group consisted of him and Vince and myself. And Ed Steskal, who had worked with Jake for many years, had moved to North Carolina State University. And so they were going different ways. And so anyway, so the way it came about was simply Mark said, hey, he's looking for a position. I applied and I visited, and, it worked out pretty good. So,
then you and Professor Schaefer developed this lovely pulse sequence REDOR, and tell us more about it. How it was born. I mean, what was the story behind this amazing pulse sequence?
Yeah. So when I joined his group, so Jake had branched. I think when he originally started at Monsanto was a big polymer company at that time, and he was pretty famous for polymers and whatnot. But he was starting to, as Monsanto was as well. So Jake kind of started moving also into biosciences, and as we know, that's eventually where Monsanto wound up. And so he was starting to do bio stuff, and I think if my memory is right, and I was looking at some old notebooks, so I think it is. Mm-hmm. He first, when you start off as a postdoc, I got to learn all of his machines and everything else, how to use things and whatnot. And once again, I lucked out because his instruments were also home built. I didn't have to patch cord everything together. I think they were based off of a Nicolay pulse programmer or something. And but still, the RF sections. Oh, and the other person that was there at the time was also, I don't want to forget to mention him, is Bob McKay. So Bob McKay, or Robert was his formal name, was Jake's RF engineer. Mm-hmm. He built a lot of the hardware and probes. They were built very hands-on lab type operation. And so I think Jake initially put me on to looking at some samples that he had gotten from Carl Kramer, who studies insects in Kansas State University. I think he's an emeritus professor now. Mm-hmm. And but I was just simply taking spectra at that point. He'd hand me these samples and tell me go do CP mass and whatnot. And so I was getting familiar with the the goings on in the lab and everything. And every day we'd go to lunch down at the research facility at Monsanto was pretty big. So they had their own cafeteria and everything. So we'd go down there and eat and stuff and whatnot. And but anyway, but before that, so anyway, we had these, and during lunches, those were just general conversations. It's whatever came up. Most of the time, it had nothing to do with NMR. It was just, talk about the weather or whatever, because it was just the time to eat and move on. But very quickly learned. So the way Jake was trying to get information, structural information, was they were using an experiment called double cross polarization. And what it is, as an example, so they would get these samples, and they would make some themselves as well, but they would C13 labeled, N15 label samples. And they were trying to, then something happens, and you want to see if the nitrogen's bonded to the carbon, or certainly is very close to it or whatnot. So they use this experiment, double cross polarization. So where, as an example, maybe you would cross polarize the carbon nuclei, and so there's your first cross polarization, just to enhance the carbon. And then you would take that polarization and try to transfer it to nitrogen. And if it transferred, then you knew that nitrogen was close to carbon. Right? If it didn't, well, it wasn't close to carbon. At least you got something out of it. But it wasn't very quantitative. I think you could get proximities, but as far as getting a number, how far away, and certainly a longer range distance was very problematic because it's a simple cross-polarization method. And so, I just kept thinking about it and everything. And so one day, and then it dawned on me, because I was starting to learn about magic angle spinning and everything, because everything he did was magic angle spinning. So, I was starting to understand the experiment a little better and everything, exactly what what I was really understanding is what averaging processes was taking place with magic angle spinning. And you could see that. But when I took Mark Conradi's course as a graduate student, I don't remember if he ever talked about the experiment or not in the class, but I remember reading it in Schlichter's book. There's an experiment called REDOR, which is for static materials. It's a very simple pulse sequence, and it recouples dipolar coupled nuclei. And I remember this experiment from either Mark talked about it or I just remember reading it because it was in the book or something. I don't really remember which, but I remember that experiment that you could, and if the goal is to find out if something's near the other nucleus, it's the dipole interaction that's going to tell us, especially in the solid state. And with an experiment like REDOR, you don't have to be directly bonded or anything else. You just got to be close. And so I remember at lunch one day, I mentioned this to Jake. I said, how about we try a variant of REDOR and try to use that idea to recouple the nuclei, not with these long cross-polarization pulses, but with just a simple pi pulse or a train of pi pulses, whatever it's going to take, right? And in fact, before I mentioned that to him, I think I actually Xeroxed that section because I still had the book. It's it's not a very long section in his book. It may be longer now because I can't remember if I was using the first edition or second edition. The third edition of Schlichter is pretty big. The REDOR experiment's still in there. But it was just a couple pages. So I Xeroxed it and I handed it to Jake, said, why don't we try to do something like this? And so he took it, and that was at lunch. And then the next day he comes by and says, yeah, why don't you give it a shot and see if it'll work. And that's basically how I got started. And so I just got on the spectrometer. And so again, in some sense, being very lucky, right? Because the spectrometer and the triple resonance probe is already built for solid state. We take those things for granted today. I do not know, I don't think there were that many triple resonance solid state NMR probes back in the mid 80s. Right, so I started in Jake's lab in '88, and he may have been the only one that had one for all I know. There certainly weren't many. If there were, it was something people had made, and it would be my guess. So anyway, he had the experimental hardware there. I knew what he wanted to do, and that was to try to get structures using isotopic labeling and things like that. But it really wasn't, you could get some information with double cross polarization, but you really couldn't quantitate it. You couldn't get longer distances, I don't think, with it. But you could get some information. And so I just happened to remember this REDOR experiment. I thought it would work. The spinning, now obviously you have to understand what magic angle spinning is doing in order to, it's not, you can't do it with a single pulse like CEDOR. It won't work. Okay. And, but it did not take long for me to figure out what to do, especially. So I did not sit down. Let's put it this way. I did not sit down, draw a pulse sequence and say, this is the way we're going to do it.
Yeah.
And I had in my mind what we would do. I just got on the spectrometer and started doing things. And I was very lucky. So, and this was on a 200 megahertz spectrometer that he had. And I just started doing, take a cross polarization proton to carbon. And fortunately, he had lots of samples, you know, and everything. Put a sample in there and started saying, well, I think, you know, we just have to interleave these pulses. And because you knew that if you only put pulses every rotor period, well, the spinning itself was already averaging the dipole interaction, so it wouldn't do anything. So you knew you had to have pulses in between as well. And so I just made a sandwich, the simplest sandwich you can imagine, a pulse every half rotor period. Okay. And in fact, I don't know if you can see it. I found my old notebook. Oh, this is the wrong one. Here it is. It's a very small notebook.
Oh.
In fact, it's a stenographic notebook. And I can tell you when the experiment started, I think.
So this is the original notebook you have? I mean,
yeah, that's the original. So there you go. I don't know if you can see it.
Yeah.
May, what, 14th? Is that it?
Yes.
Oh, wow. That's my second son's birthday.
Hey.
Unbelievable.
Amazing.
I just now realized that. My second son was born on May 14th, not 1987. But wow.
Wow.
So that's kind of funny.
Yeah, yes, it is.
But anyway, and this is just writing down the parameters for the spectrometer. The next page, it doesn't show the pulse sequence. That was just written on some paper, but it does show the files. So there's the first file, and REDOR, you do a delta S over S experiment, and you can see the delta S over S ratios over here. And I just started playing with phases of the pulses.
Yeah.
And the absolutely beautiful thing about this was, so there it is, the first page of data there. And this was done on an asparagine sample. And but the wonderful thing about this is that on Jake's spectrometer, there was an oscilloscope mounted on the spectrometer. You could see the pulse train on the spectrometer. Okay. Again, you were not programming like you do now, and you see, a beautiful pulse sequence on your screen, right?
Yeah.
That didn't happen. You had to pulse program as Nicolay pulse programmer, and they were just by putting in a bunch of numbers. But on the scope, all the pulses would show up. And it's an oscilloscope, so you knew the spacing and everything. And he had some switches where you could toggle. If you want to see whether phases right and everything, you could just turn them off and then flip them back on. Okay. But more importantly, so you could see on one channel the pulse sequence. Every shot, every time that thing went off, you saw the pulse sequence. And on the next channel, you could actually see the free induction decay. Okay, in real time.
Yeah.
Okay, not looking at the computer. You saw each scan. Now these were labeled samples, so the signal was big. And the very first experiment I put in there, I can tell you, I must have been grinning ear to ear because, on the one hand, you're like, I don't know if this will work or not. I think it'll work. Who knows?
Yeah.
So I'm looking at the oscilloscope, and so it's a 2-block experiment. In the first block, you don't have, if we're observing carbon, you don't have any pulses on the nitrogen. So I see this big signal come down. The next scan is you now apply the nitrogen pulses in this case. And I kid you not, big signal, next scan, small signal, big, small, big. I mean, I probably fell out of my chair because it was just so obvious. I mean, it was clear that it was working.
Yeah.
And because, you could test, well, let me just turn off the power to the nitrogen amplifier. Well, in that case, both channels would just stay big, right? And everything. So the very first experiment I ran on the thing worked. So it couldn't get any worse than that, right? So, So then it's just a matter of optimizing the thing and everything. So you knew immediately that it was working.
Yeah. So at the time, once you saw the result, I think you immediately knew that it's going to make a big noise, isn't it?
Well, because again, the background is you already knew that this idea of trying to probe distances between different nuclei was important because Jake was demonstrating that with the double cross polarization, things like that. So you knew that there was a place for these things. And now you realize that I'm pretty sure we should be able to quantitate this and we wouldn't be limited by in distance. Well, you're limited to somewhat. How long can you hold the signal together?
Yeah.
But you would certainly be limited to not things being bonded or nearby or anything, but they don't have to be bonded and they could be far away. And it didn't take us long to, because he had plenty of samples to realize, oh, we can go out actually pretty far with this. So, yeah, you kind of had a gut feeling that this was going to be useful. There was no doubt about it. So, uh, and but again, it would also require people to have the hardware to do this because these are, in a sense, triple resonance experiments, right? So you're going to have to, if other labs want to do it, they'll have to invest money in it and things like that. And of course, people did and so forth. So
Yeah.
But I think it was pretty clear just from the previous work that there was that it would have a usefulness to it.
Did you first publish it or you presented it in a conference? I want to see how the community, the NMR community responded, how they received it, what was the reactions?
Yeah, it was published very quickly as a note. So it was presented in a conference a year later at an ENC in Rochester, New York. I don't remember off the top, and I don't have it in front of me, the exact date for the paper that came out. But it was published as a note because, one, it's short and would come out pretty fast.
I would like to know whether you keep up with the pulse sequences that have been developed based on your pulse sequence.
I wouldn't say I keep up with them so much as far as the pulse sequences go. I think the way I kind of it's more like through applications because I'll see people write an interesting paper on something that uses it, and they'll put their own spin on it, so to speak, right?
Yeah.
And so it's I don't really, I guess, focus too much on the pulse sequence itself, but when people apply it to something as it is, and just looking at where it's applied and how interesting those projects are, that's what I find more interesting, I guess. And then if they put a novel spin on it or make some adjustments to suit their needs or to make it better and so forth, it's then it comes out in their publication. So that's more or less where I look at things. I don't necessarily go looking for pulse sequences just for pulse sequence sake so much. It's like, how is it applied and used?
In glass science, it turns out that it's very, very useful and beneficial because we don't have long range order, and these short range orders are actually these short range orders are detected very nicely with REDOR pulse sequence. So is there any other kind of applications, any other types of applications that amazed you? The work that they used REDOR to answer a question, to do a project. Do you have anything in your mind?
Well, I don't think I have anything because I think all of them were very interesting. But I've known Helmut for a very long time, and I couldn't think of a harder system to study than glasses.
Yeah.
I remember seeing his early, especially early on, because he I think was a fairly early adopter of REDOR in the study of glasses, or just in general. He very quickly started using it. And all I could think was, man, that is one messy system to focus on. And but obviously he stayed with it and everything, and it's gotten some very useful information, as have others. You probably again incredibly complicated because, like you say, the order is just simply not there. Maybe locally it is, but on a bigger scale, so you're dealing with a very difficult situation.
So before we move to beyond the lab, I would like to ask another question, not about the research, about the teaching part of your career as a professor. What do you teach, and what courses are you teaching?
Oh, I teach mostly, on occasion, freshman chemistry.
Mm-hmm.
And when I say on occasion, the last time I taught it was probably 5 years ago.
Mm-hmm.
Okay. But primarily I teach physical chemistry here.
Okay. So let's move to beyond the lab. So I
Well,
would like
before
to.
we go, though, outside the lab, I did want to show you one other plot.
Yeah.
Because we worked on REDOR for quite a while, and early on we realized there were problems that had to be overcome. And one of those was if you go off resonance, you could have a very high delta S over S. Just pick a number. Maybe I'm running an experiment, and if I'm on exact resonance, say with the nitrogen, and I'm observing carbon,
Mm-hmm.
maybe I get a delta S over S of say a 0.5. But if I move off resonance, it's no longer 0.5. In fact, it could almost go to 0. It disappears.
Mm-hmm.
And again, it's by understanding really what was happening during magic angle spinning that helped guide this. But anyway, we realized that's going to be a real problem because you can't be, especially if you have several labels and they're not all at the same resonance position.
Yeah.
You could get very misleading information. And so I'll show you another plot if you don't mind.
Of course, yeah, please.
This one is from 1989. So it took us a while to sort this out. And I don't know if your camera can pick it up or not.
I think so, yes. Yeah.
So this is a delta S over S plot. And the bottom, so we're observing carbon, and the bottom axis is the nitrogen N15 resonance offset. Okay, 0 meaning we're on exact resonance. Don't remember what the sample is. Could look it up. It's something simple, alanine or something. It doesn't matter. But the important thing is, if all the pulses, nitrogen pulses, are the same phase, okay?
Yeah.
You see this also. This is the data that you get.
Yes.
Notice the whiteout is there because I was cheap and I was reusing graph paper. Okay? Very severe, because here's a delta S over S of what? It is about 0.5. And you go off resonance by, I think it turns out to be about the spinning speed, because these peaks actually match spinning speeds. They're related.
Mm-hmm.
Delta S over S is like 0.1. Oh, that would be a huge difference in distance if you just believe that number.
Yes.
Clearly not right. But then I discovered this phase sequence XY4, which is the basic building block. And then in this plot, we're just using XY4. So if you change the phase, it's not just the same phase, but in an XY4 phasing scheme, now you see that the data is almost independent of offset. And that's why REDOR, I think, has become useful, because now we got rid of the offset dependence. And the way that came about, if a student is watching this, is simply sitting in front of a spectrometer. I was actually working on a different experiment of trying to determine chemical shift anisotropies using similar ideas. Could I do, it would be like a 2D experiment. In one dimension, you're spinning fast enough, you got just isotropic shifts. And in the back dimension, you have a spinning sideband pattern that's characterized by the chemical shift anisotropy. And when I was playing around with those, so I'm just sitting there on the spectrometer and I'm looking at things, and I realized very quickly then that I have a really bad offset problem. And so I was trying to get rid of it, and I started playing. I noticed certain properties. Again, this doesn't happen in a day.
Mm-hmm. Yeah.
Quite a while. But I'd see these patterns, and then I finally realized that this XY4, because I developed it on the chemical shift experiment, and actually published a paper on it. on recovering the chemical shift anisotropy, but I never mentioned the phasing scheme in that paper. But that's where the XY4 came from. And then I applied it to REDOR, and then that's when we saw that the offset dependence disappeared. And then moved on to XY8 and XY16 and all those, the super cycles of XY4. So primarily I just use XY8 now. It seems to do well enough. But the point is, I guess I'm trying to make is, it was just by sitting there and just at the spectrometer and watching signals in real time. In other words, I wasn't sitting there, let it run, disappear for 2 hours, come back. I mean, really was just sitting there, continually changing things and seeing how they behaved. Mm-hmm. And finally was able to, kludge it together that there's something. And then after that, then you develop an understanding of why it's working and everything.
What do you think is the future of REDOR in terms of applications?
So I think it's part of a toolbox for people to use. And obviously there's other tools out there. I mean, certainly since the mid to late 80s and onward, there's more and more experiments coming online. And I think it certainly has its place. I mean, people are still using it and everything. And of course, then there's other experiments. So, there's all kinds of variations and different experiments to use. So it's sort of, I think of it sort of like this, maybe in some sense. For magic angle spinning, I don't think it's going away. The technique has been around. Well, okay, magic angle spinning started, 1958? Okay, by Irving Lowe, who was at Washington University in the physics department, and Andrews. Independently, they came up with magic angle spinning. In, again, 1958. But we're still doing it, right? We're still spinning samples to this day. So, it's a tool, and everybody does magic. Nobody references their papers anymore, right? It's taken as a given that it becomes just part of the fabric of NMR, and so I think REDOR is kind of along those lines, like cross polarization. Nobody even references the original papers to cross polarization anymore or anything else. I'm lucky. I think they still reference REDOR, but the point is that those experiments, they're parts of tools that people still use, and there's other things out there, right?
So how about the high Q quadrupolar nuclei? I mean, have you ever thought about it, or have you ever worked on it since then? It has a limitation, right? The REDOR for the quadrupolar nuclei, 5-half, 7-half, to the best of my knowledge. It might be hard to do, isn't it?
Yeah, so obviously for low Q things, REDOR works just fine. So we've done experiments, say for example, with lithium, deuterium, things like that, and even cesium. So we've published papers on cesium on a clathrate, I think, and in cesium, I think it's been 7 halves. It's 5 halves or 7 halves. I don't remember.
I think it's 7.5.
Yeah, and it works beautifully. Just plain old REDOR works beautifully on cesium. But those are low. Their quadrupole coupling constants aren't huge. They're not zero, but they're not massive. So it works fine there. And then, of course, when you get to bigger quadrupole couplings, things get harder. So, we developed this experiment REDOR for rotational echo adiabatic passage double resonance. Now, most things I deal with aren't quadrupolar. And here's a side story for you. So the way that came about was at a Gordon conference. Alexander Vega was giving a talk on trapdoor. And again, the goal there was to try to recouple quadrupolar nuclei. And that involves very long pulses. In fact, I don't even think you turn the pulse off and so forth. But I was listening to his talk, and he was giving his talk, and it was right before lunch. And it dawned on me that, because then he made it clear in my mind how it was working, how trapdoor worked, and it had to do with these adiabatic passages. But by putting on long pulses, you're going through these passages multiple times. And I thought, well, things are going to crap out pretty fast if you keep doing that, if the quadrupole coupling's big. So why not just limit it and go through them once or something? And so at lunch, I was just standing in line waiting for lunch, and it dawned. I thought, oh, I think we can do this other experiment, and I think it'll be just as good, maybe better. I don't know. And but it's worth trying. And so I remember telling some people in the line, a couple of people next to me about this, and they had their doubts. They said, "No, I don't think that'll work." And I thought, well, I was pretty sure it would. And I called my graduate student at the time, Jim Jors, and told him to retune our probe down to N14 and have it set up, because I was still up. The Gordon conferences in New Hampshire, and so he retuned the probe. And when we got back, we tried. It worked the first time, and so anyway, and on nitrogen, so something with a reasonably substantial quadrupole coupling constant, and worked pretty well, and so forth. So now, and we've applied it to oxygen O17, and it works there, and that has a reasonably large quadrupole coupling constant. So it certainly works for oxygen and for N14.
Let's move to beyond the lab. So what do you do in your spare time?
Oh, well, I bicycle most days, and I run most days. Go running in the mornings and bicycle in the late afternoons, evenings, and then basically hiking and camping. Pretty much anywhere outside is what I'm doing, probably. So,
Okay.
and yeah.
Yeah. And what was your dream job when you were a kid? You said you didn't have in your mind specifically what you are going to do, but when you were a kid, did you have anything in your mind, any dream job?
No, well, as a kid, I just remember knowing that I wanted to do science. I was just attracted to it. From my earliest memories, I didn't know exactly what, obviously, but I was just somehow knew that's kind of what I would do. So in some sense, I think I have my dream job. Every day, I'm really very lucky. The way I look at it is, I've been very fortunate. So I enjoy what I do every day, and can't really ask much more than that. It keeps you busy, and this is the beauty of NMR, I think. As far as dream jobs go for me, is again, I started off in physics, then of course a postdoc with Jake in the chemistry department, and again, the only chemistry I'd had before that was freshman chemistry. That's all I know, right? But you start seeing the applications and things, and you start familiarizing yourself with them and learning a little bit and so forth. And now the stuff I work on is, we still do some stuff with materials, but also got some biological projects going on as well. And so, in some sense, I guess I couldn't have asked for a better dream. Maybe I got lucky by choosing NMR because it allows you to be so flexible. You're not locked into just doing one thing over and over again. And
It's
you can
very collaborative, right? You get samples and you need to work on different projects. Yeah, it's very interesting in this way. If in another world, in a parallel world, if you can pick another job, what it would be?
I was telling my son the other day, I think if I had to have another job, it would be an engineer on a railroad train. Driving the train, because it's outdoors. You're not stuck in a factory or anything. I think physicists maybe are naturally attracted to trains for some reason. I have several friends that actually do model railroading and things. And
So if there were a time machine, would you rather go 100 years back or forward?
Well, that's interesting.
Hmm.
Uh, I think I'm happy where I am.
Just to
Uh,
visit, I don't mean that you go and live over there. If you want to just take a look or have a
well,
trip.
certainly, if you went back in time, uh, especially if you were interested in nature and things like that, where it was more pristine. Obviously, in 100 years, it wasn't pristine everywhere, uh, but you would certainly find more places where it was.
Mhm.
I think that would be very interesting. I'm not so sure things will be so pristine in the future.
Yeah.
Uh, Especially, again, I kind of like the outdoors. So, uh, so going back in time and seeing places that were more wild, assuming I didn't get eaten by something or attacked by something.
Hmm.
It'd certainly be a very interesting thing. I mean, there's still places, even in the United States, you can go and still see the wilds and things, but it's obviously nowhere near what it was
Yeah.
even 100 years ago. Yeah, I mean, if you look out west, it wasn't that well developed.
Yeah.
Maybe I'd go 200 years ago,
Yeah.
and
Where do you go to see the nature? Where you want to see?
oh, I would always head towards the mountains, I think. So,
Mhm.
uh, you know, uh, we go out west to, the Rockies and such pretty
Mhm.
frequently. In fact, last year we went out to the San Juan Mountains and did some camping and hiking there.
Yeah.
And so I've been going out that way for many, many years. And the year before that, I think we went up to the Dakotas to the Theodore Roosevelt National Park
Mhm.
in way out in the middle of nowhere in North Dakota. And it was very interesting and so forth. So I kind of like those mountains, but I also like the Appalachian Mountains, which is the mountains that we live in. Uh, you don't have these, bigger peaks, but it's just a different experience altogether. It's all forested and everything, and lots of streams. But you have those out west too. So, uh, but even it's interesting. Like, and that's why you'd probably want to start at one end of the country and walk all the way across if you had the time to do it, because we always drive. I'm not a big fan of flying. I fly if I have to, but if I
Mhm.
can drive somewhere, I'll just do that because I'm slow and I can see things.
Yeah.
And driving across, and you stop in the plains of the United States, so Kansas, the Dakotas, and it's different, and you appreciate it. It's like, oh, this is not what I'm used to seeing, right?
Mhm.
And the wind and things like that. So it's all very interesting. And it would be very interesting just to pop back 200 years ago into the plains where there's no one around. Well, there were obviously people around and so forth, but there weren't millions and big cities and just something wide open, right?
Yeah.
And so I think I would choose the past in the sense of not that the past is better, but as far as nature goes,
Yeah.
who knows? Maybe we'll get lucky and someday it'll get back that way. It would be
Yeah.
nice.
Yeah. Yeah. It would be nice. So, do you have any regret in your life or in your professional life?
I have zero regrets.
Amazing.
Oh, it's I like I said, I think I've been very lucky. I've worked with great people that's been very helpful to me, and in some ways, I think I just kind of fall into things. So, um,
So, is there anything that you say I don't regret, but I would like to know when I made a decision, what would be the path if I chose another thing. When you made a decision for, I don't know, graduate studies or major, what if you chose something else? I mean, is there anything in this sense?
yeah, I again, like I say, even as a kid, I knew I was going to do science of some kind,
Hmm.
and and I just kind of followed that path. I mean, it worked for me, uh, and at one point,
And as the last question, who's your favorite scientist in the history?
oh, it had to be hands down Michael Faraday.
Hmm. So, for any specific reason or?
Yeah, if you think about it, well, the way I think about it is, Michael Faraday, he had no real formal education. If you read the history of Faraday, he just started off working in labs, but he read a lot. I think his early career actually maybe worked with a bookbinder or something. But it wasn't like he went off to college and learned all these fancy theories and everything. But he learned things on his own, and obviously learned them very well. And and it was extremely good in the lab and everything. And and think about it, where did the concept of fields come from?
Mm-hmm.
It came from Michael Faraday. I mean, that was a huge breakthrough in science, is the idea of a field, and so forth. And that just came from his own intuition. The guy obviously had an incredible intuition about things. Uh, he didn't describe the mathematics of it so well. I mean, that took Maxwell to really put everything together, from what Faraday did and Ampere and other people. But the intuition he had of how things worked and how nature worked was very incredible, and so forth. So I just find it absolutely fascinating that someone, and I think he made these points. Science is available to everybody, and if you just sit there and do it and get your hands dirty, and because I think that's what it takes half the time, and that's what he did. And my little contribution to Faraday is, what he also believed in was that science should be given to the public. And he had these famous, what do you call it? I think they were called the Christmas lectures.
Mm-hmm.
And so once a year, he would give these lectures that were open to the public, and he would demonstrate certain things, scientific things. So think of this in the 1800s, all right?
Interesting.
Certainly no internet then.
Yeah.
And there were no movies even. Jeez, think where we are. And so people had to go to some place to actually see something like that. And he started that. And those lectures still continue today, where he started giving them. I mean, obviously, he's not giving them, but the tradition is. And so 20 some years ago, I started doing something similar, clearly not of the class of him, but I once a year do these, I call them the children's chemistry show. So in December of every year, we have this, I started it in our department where we open it to the public in our big lecture hall, and we just do a whole bunch of chemistry demonstrations. Now, usually it includes blowing up things, fireballs, making a mess of everything, because it's really aimed for children and hopefully getting them excited about chemistry. And then we had some hands-on things, but we spend the first hour just demonstrating various things, and I think a fairly fun and interesting way. Basically, make a mess and blow things up and whatnot.
So, is there anything that you wanted to say I didn't ask?
No, I don't think so. I just think again, I just say it again. I think I however Mark finagled me to get into NMR, I guess I'm grateful because it's a powerful technique. It's very flexible. As everyone who's done NMR has shown, it's only, you use your imagination. You can do all kinds of interesting things, solve interesting problems. And there's all kinds of techniques out there. And so I've been fortunate, and hopefully will continue to be. I still have graduate students, and they're working on interesting things. So things are going pretty well, I think. Yeah.
Thank you so much, Professor. Thanks for your time, your insight, and thanks for showing your notebooks. And have a great day.
I really appreciate you doing this. So
Yeah.
Appreciate it very much. It's a lot of time on your part as well.
Yeah. Thanks. Have a great day.
All right. See you later.